good afternoon, and welcome to Maps for Good, saving trees and saving lives with petapixel scale computing. I just love saying that word, petapixel. How's I/O going for you guys? Yes? All right. Well, in my opinion, we've saved the best for near last. My name is Rebecca Moore. I'm the engineering manager on the GEO team. I lead two projects. Google Earth Outreach, which is our program that works with nonprofits and indigenous communities all over the world to foster the use of Google's mapping tools to make the world a better place. And then also, several years ago, I started the Google Earth Engine project, which is what we're going to focus on today. Both of these were 20% projects that are now thriving teams, so go Google. So we're going to talk about a couple things. First of all, what is Maps for Good? How did it get started? I want to introduce you guys to not only Earth Engine, but the whole field of geoscience. A lot of times when we talk about Earth Engine, we're talking to specialists in so-called remote sensing. I think a lot of you guys are, Android developers or whatever, so there may be some new concepts. We'll crack open Earth Engine, look under the hood at how it works, why it's so amazing. We actually have experimental APIs that we'll demonstrate. Then we're going to talk about some of the really exciting projects that our partners are doing that are making the world a better place using Earth Engine, and finally show you how you can get started. So how did I get started? I'm not an activist, I'm just a computer science nerd, but I live in this beautiful place in the Santa Cruz Mountains, and one day back in 2005 in the summer, I opened my mail and I got this. Okay, what does it say? So I'm a map geek, so I studied it. Notice of intent to harvest timber, non-industrial timber management plan area. The legend was not that helpful. If you look at it, it sort of says black lines tell you what's going on. Well, the whole thing's black lines. So there were a couple thousand of my neighbors and I that got this notice in the mail, and most people threw it out because they couldn't understand it. But Google Earth had just launched 2 months earlier, and I had been playing with Keyhole before that. And I thought, well, what if I wanted to understand what this map was saying? Because I was worried that my community was threatened. We have the largest remaining stand of old-growth redwood trees in Santa Clara County. It's a beautiful place. So over one weekend, I opened up Google Earth, and I found the same place, and I started bringing in the elements of the plan onto Google Earth. Where the helicopters were going to land and take off, where the logging zone was going to be, how close it was going to be to schools, daycare center, nursery schools, and so on. Google Earth also, of course, gives us 3D. So we had just acquired SketchUp, and one of my colleagues helped me make a 3D model of a helicopter on a bombing run over the schools. Anatomically correct helicopter, actually, tree to scale. But because, in fact, the plan was proposing, because the land was so steep, they couldn't get the logs out by road, so they were going to be helicoptering over the community in perpetuity. So this was actually the same time when Al Gore was going around with An Inconvenient Truth. I had a much smaller audience, but I was being asked to present this Google Earth visualization and the animated flyover to the newspapers, to the politicians, to members of my community, to the Sierra Club, because no one could understand that 400-page document and read those grainy black and white maps, but they could understand the data in Google Earth. And eventually, it took 2 years. There were a lot of battles back and forth, but using Google Earth, we not only showed that the plan was a bad idea for fire safety, water pollution, endangered species, and so on, but actually that it was illegal. We used Google Earth to prove that the plan did not even meet the requirements for consideration. And so we stopped the logging using Google Earth. Here's where you're supposed to cheer. Yay! So that got a lot of attention in the media, and I started to be contacted by nonprofits all over the world. Teach us what you did. It was one of the earliest grassroots environmental uses of Google Earth. And so long story short, as my 20% project, because at this point I was now a Google engineer on the Google Earth team, another story there, as my 20%, I said, hey, can I be the liaison to the environmental community and help them understand how to use our tools? And with several other Googlers, we started what became Google Earth Outreach. We now have more than 5,000 nonprofits all over the world that are, they're using Maps API, creating KML, Street View visualization. They're doing all kinds of things using our tools for conservation, human rights, disaster response, cultural preservation. There's some amazingly beautiful projects that people are doing. So there I was in the Brazilian Amazon in 2008 because an Amazon chief had actually come to Google the year before and asked for our help to teach his people how to put themselves on the map, literally because this was his territory and it was under threat. There's illegal invasions of his land happening that you can even see in the satellite imagery. And when he saw that in Google Earth, he was the first member of his tribe to go to university, he said, this is the tool that will raise awareness with people around the world of the threats my people face. And he told his tribe, the time has come to put down the bow and arrow and pick up the laptop. But while we were there, we also met with a Brazilian geoscientist. And he said to us, Google Earth and Google Maps are great, but in fact, the Earth is changing dramatically. This is deforestation in the Amazon over a couple of decades. That pattern is very typical. They were losing more than 1 million acres a year of Amazon rainforest to often illegal deforestation. This scientist had the methodology to analyze daily satellite data coming in and automatically detect areas of suspicious change and alert law enforcement, because the law enforcement on the ground was very skimpy. But the problem was, it was like terabytes of data. It required weeks of processing on his desktop. By the time you would get the results, it was too late. So he said, Google, you have Google Earth and Maps. You let us look at the data. How about if you let us measure, monitor, do science, right? And do alerting on changing phenomena on the Earth's surface like deforestation? Well, that was a pretty cool challenge, and so we decided to do that. That was the inspiration for Google Earth Engine, that you can not only look at the data, the imagery, but you can analyze it. And so we think of Earth Engine as deriving information from all of this data that is around us, but has not been thoroughly mined for useful information for people and for the planet. So for example, there are a ton of satellites. This is just NASA's satellites that are orbiting the planet as we're sitting here, working very hard, collecting lots of data, and not just pictures of Earth, but scientific measurements, right, that could relate to weather, heat, all kinds of things. And one example sensor is the Landsat satellite. It's been orbiting, that program has been orbiting Earth for more than 40 years. Every 16 days, it completes a pass and it starts all over again. It's never had a break in coverage. There's more than 3.6 million images of Landsat data in the archive, and it's a treasure trove. And that's just one example. Now, I said that it's not just red, green, blue pixels. It's not just RGB. And I want to say a little bit more about that, because here's where the interesting geoscience comes in. So let's go back to high school physics, right? We know the electromagnetic spectrum. So there's the visible light to human beings, red, green, blue. And then beyond that, there's infrared and other bands. Well, these satellites are actually taking measurements across all of those bands. So, for example, here is a Landsat image right near Burning Man. All right? There's various things going on in that scene. It's kind of hard to figure out. There's clouds, there may be snow, there may be grass. It's hard to tell. Very, very typical satellite image. That's what you can see with the red, green, blue bands. But if instead you use the red and the near-infrared bands, you can discriminate vegetation, growing vegetation. And that shows up here in the dark green. Or if you're interested in snow and ice, you can look at the green and the mid-infrared band, and that does an excellent job of discriminating snow and ice versus everything else. So this kind of data is important for us to store. So we became committed to storing all of this these spectral bands of information. Now, so there's the nature of the data, and then there's the scale of it. So I mentioned Landsat is a huge archive. It comes off the satellites, and it goes onto tapes in a vault in South Dakota. It's very secure. But the problem is it's difficult to get access. And until 2008, it cost $600 a scene. So scientists used to say, we would do the science on the data we could afford, not the data we needed. But in 2008, the US government enlightened data policy, made all of Landsat free. Suddenly, the historic archive and the data being collected every day, massive amounts, is now available suddenly for data mining. How could you possibly handle that on your desktop? You can't. This is where cloud computing comes in. So with Earth Engine, we decided to focus on 5 or 6 of the most important satellites that scientists were telling us would be transformative in advancing science, natural resource monitoring, if we could get that data out of those dusty archives and online and available for analysis. So that's what we did with Earth Engine. And when you look at this data center, there's really 2 things about this that are important for Earth Engine. First, the storage. We're now storing petabytes of this satellite and other environmental data coming in every day. And then the compute resources, massive compute that's co-located with that storage. So when you have all the data and you have this compute, what can you do with it? Well, for example, most scenes look like this. This is, I think it's Borneo. But if Landsat collects, let's say, 20, 24 images a year, well, the clouds may be over 1 pixel in one image, but clouds move around. They won't be over that pixel in another image. If we have all the pixels, we can select the best pixel from a stack, and we can composite a complete cloud-free image. Here's another place. This is the Isle of Mull in England. And this is after we composited and removed all the clouds. It's like magic. South America used to look like this in Google Earth and Maps a year ago. Not that great, to be honest. But after we applied this technique to all of South America, it looks like this now. And in fact, last spring, we did it for the whole planet, and we launched the first 15-meter global cloud-free satellite base map of the planet. And that is what you see in Google Earth and Google Maps when you open them. And that was created by Earth Engine. Okay, so that was one time period. The dates of those images were approximately, the pixels that we used to make that cloud-free mosaic were approximately 2012. We went back a little earlier if we had to in really cloudy areas. But then we did the next project. We said, well, we have all this, we have like more than 30 years of data. What if we could create essentially a cloud-free image of the whole planet every year? And then stitch those together into a seamless online animation that you can navigate. So we built that. It's called Time-Lapse. We launched it last May. And it's an HTML5 video animation of the entire Earth, where as you fly in, instead of in Google Earth and Maps where the world is static, it's animating underneath you from 1984 to 2012. And these are some of the phenomena you can see. You can see glaciers retreating, crop circles of irrigation appearing in the desert of Saudi Arabia, these artificial islands sprouting off of Dubai because the tourism agency wanted more beachfront, and deforestation in the Amazon. But we're not limited to this. You can go anywhere in the world in time-lapse, and you can find interesting things. Here's Las Vegas. What do you see? Las Vegas was the fastest growing city in the US during this period. What jumps out to me is Las Vegas is growing, but Lake Mead is shrinking. And that's pretty obvious. You can see that in just a few seconds. So Time magazine was really excited about this, maybe because their name is Time. who knows? But we worked with them actually as partners to launch this on their site as well. And they did a whole series of science and environmental reporting of the phenomena that you could see really for the first time in time-lapse that help you understand things like urban expansion or desertification or climate change. Now, what I wanted to point out is the kind of compute that was involved. So this was almost 30 years of satellite data. We analyzed more than 2 million Landsat scenes. It was almost a petabyte of data, 909 terabytes. It took 2 million hours of computation, but we sharded it over 66,000 computers, and so we had the result in a couple of days. I think it would have taken 300 years or something if we had done it, tried to do it on a single computer, if it never rebooted in those 300 years. So those were visualization products, but the heart of why we built Earth Engine was for science. This is Carlos Souza. He was the scientist who originally inspired us. That was his system called SAGE, Sistema de Alerta de Desmatamento, for detecting and alerting on deforestation. He's now built, he's really our first power user, our first launched application running on the Earth Engine API and backend to monitor deforestation in the Amazon. It's a very cool Canvas app that allows you to change the temporal range on the client, and you see the patches, those red patches of deforestation that show up depending upon what occurred during that time range. Every month, he publishes a bulletin that goes to law enforcement, to Brazilian law enforcement authorities on what has been seen using Earth Engine. And he reported to us that it's cutting in half the time it used to take. And moreover, now he can give it to all these other countries in the Amazon basin and around the tropical forested belt of the world who've been wanting that, but they didn't want to deal with running a software package from this researcher. Now that it's online in Earth Engine, they can all have access to it. Back in the US, we did a project with Matt Hansen, who's a leading scientist in analyzing Landsat data, and that was detecting forest change in Colorado in 2010, finding things like pine bark beetle damage, wildfire damage. We then went global with Matt Hansen and created the world's first high-resolution global map of deforestation from 2000 to 2012 at 30-meter resolution. You would think that people would have known where forest was and where it was disappearing, but in fact, there are many, many countries in which there was complete ignorance. So that's what it looks like. It was published in Science magazine. We've had thousands of institutions now downloading the data and doing different kinds of analysis on, well, how does this relate to national parks? Are those parks actually protecting the landscape or not? Oh yeah, I should say about this, this was 1 million hours of CPU on 700,000 Landsat scenes. We ran it on 10,000 computers in parallel, so we had that in less than a week. That one would have taken 15 years. So the ideas were like turbocharging this really great geoscience for the benefit of the environment and the benefit of all of us. Here's an animation that shows you some of the data in the data set that we produced. This is the island of Sumatra. You see the advancement of deforestation, including encroaching on their supposed national parks. And now the final step with this project is World Resources Institute has used this data as the base map for a monthly alerting system called Global Forest Watch. You can go to globalforestwatch.org, where anyone can find out what's going on in near real time in a forested place on the planet. You can subscribe to a place you may be interested in. Businesses are using this, governments, media, and so on. So we're happy about that. Okay, let's crack open Earth Engine. So this is sort of a typical top-down, bottom-up thing. At the bottom of Earth Engine, we have this massive public data catalog that we're updating every day. And we keep adding to the data sets that we host based upon demand from our community of users. On top of that, we have two kinds of computation, either interactive, on demand, or batch, when you have a really big job like those 1 million hours of computation for the whole world. We have REST-ish APIs, but in fact what our users really are developing against are our client libraries in JavaScript and Python that have about 600 functions now that do image analysis and do vector analysis, or fused image and vector analysis. And finally, on top of that, Google has built a couple of apps, and we've got this growing community of users that are building this. We're still experimental, but we have now a couple thousand developers on our API. So this is kind of going through some of the data. I've mentioned Landsat, but there's MODIS, there's elevation data. You can do a lot of interesting things when you know elevation. Weather data we're getting every 3 hours, fire data, and so on. Another important point that's kind of small on this slide, if you have a Google Maps Engine account and you're uploading your own data, raster data, or soon your vector data, you can analyze that from Earth Engine, privately, securely, right? So that's kind of good. You get access to both public data and your own private data for analysis. All right, so what can you do with Earth Engine? Well, at the most basic, you grab an image, your image or one of the images from our catalog. You can then apply an algorithm to it. This may be one of our several hundred algorithms we've provided or our scientific community has contributed, or maybe one that you've written yourself. You can also filter a collection of images by date or by geography, by metadata. And this is actually where it gets much more interesting, because if you're just analyzing 1 or 2 satellite images, don't come to Earth Engine. We're like the Large Hadron Collider when you need like a little telescope or a little, I don't know what the analogy would be. But where it gets interesting is when you're trying to operate over massive amounts of data. So you apply the algorithm to the whole collection, and then you can reduce it to a single image. This is truly MapReduce. And finally, you can do aggregate statistics over that. Yes, truly MapReduce. Someone laughed, okay. I mentioned, and I'm going to kind of speed up a little bit here because I want to get to the demos, but there's on demand, you'll see, we'll have some demos of this, interactive from our IDE or through the API. If you have a really big job, you can do a batch job, which we run at lower priority, so it's very efficient. We parallelize, right? All of those functions are intrinsically parallel. So imagine there's some area you're trying to analyze. We split it up, right, into 256 by 256 image tiles. We distribute those to thousands of computers if need be. Each one performs its part of the computation, the algorithm. Under the covers of the API, we stitch it all back together, and there you go. All right, some code. Remember I told you could, like, we were removing massive amounts of clouds and producing that first global cloud-free image? You can do this too in 4 lines of code. I hope this blows your mind. Okay, so if we walk through this, and we have JavaScript and Python, the first thing accesses you select an image collection. This is requesting the Landsat 7 satellite. We're filtering it down in the next line to a range of dates from January 1st, 2011 to December 31st, 2012. The third line is where the magic happens. It says median image equals is filtered.median. What we're doing there is for every pixel and every band, we're finding that median. And the statistical median tends to rule out clouds, which are very bright, or shadows, or data gaps, which are very dark. And you end up getting a very nice representative version of that pixel. So we're doing statistics on the planet, which you can only do when you have massive amounts of data. And then finally, adding it to the map. And the other thing I should point out is when you write this code, you're creating an expression, it's almost Lisp-like, that's a functional expression of something that will undergo lazy evaluation. We store that code. It's applied when you use our interactive IDE to browse around, and it runs it on demand or in batch mode. All right, demos. So we have 2 front ends. One is our workspace GUI that's really well designed for classification. This is our home page. If you go to earthengine.google.org, you'll see a series of interesting data products that have been produced. There's a data catalog that you can browse. But now what we're going to do is use Google's machine learning infrastructure, which we've wired in into the back end of Earth Engine. So, YouTube did a major machine learning on the corpus of YouTube videos, and they found that there's a lot of cats, right? Well, I'm really curious to see what people find in all the corpus of satellite data. Anyway, so what we're doing here is first choosing a range of dates that we want to classify. What we're going to try to build is a classifier of forest versus non-forest. And literally, you can do it in a couple of minutes in our workspace. We're creating the classes. You could have 2 classes, you could have 10 classes. Of course, the more classes you have, it puts a burden on, can you really discriminate those different classes from one another based upon the data? Remember that we're not just analyzing the 3-band RGB data that we see here, but underneath that are multiple bands. In the case of Landsat, it may be 10 bands, depending upon which sensor. So now we're going to train it by putting down, here are representative spots in this image that are forest. You can do this by dropping a place mark. You can create a polygon. And later, the machine learning infrastructure is going to try to extract what's the pattern there. As distinct from, now we're putting markers down for non-forest, looking for those places that are clearly not forested areas. Google's machine learning backend has a whole series of different methods you can use, CART, random forests. We're going to use the fast naive Bayes because it's fast. And it actually does a pretty good job. So what we're doing now is we're training a model. And you can see in the upper left, and there we go. And I did not speed this up. This is actually the way it works. It's now built that model. It's applied it to what we're looking at. And as we zoom out or pan around, here's that just-in-time evaluation. We're now applying that model throughout the Brazilian Amazon. And Chief Almir now has classification of forest versus non-forest. So that's the GUI. Now let's look at the IDE. You remember that code on cloud removal. It's a simple IDE, but we have a series of examples for vector and raster analysis that are built in to help you get started. There's a code editor that has tips if you're missing your semicolons. We have built-in documentation. When you hit run, that's when you actually cause your algorithms to run over the area that you're looking at in the viewport. And finally, this is really important, the get link allows you to say, okay, I really like this. Give me a link. I'm going to share it with someone else who's an Earth Engine trusted tester. They'll open it up, and they'll see exactly your analysis on the data, and it will run for them. It's a great way to collaborate. So now we're actually going to run a cloud removal. The first thing I'm going to show you is bad data. So I think the first image here is 1 week of Landsat 7. There was a defect in the satellite that has these scan line gaps. 22% of the pixels are missing. There's clouds. But now we're going to bring in that cloud removal code. This is what you get this is the South Bay. And if you pan around, you would see this elsewhere. Here's another example of, in this case, we're going into that area of Burning Man, and we're going to show those different types of information you can extract from the same fundamental set of imagery, just looking at different bands. That's the RGB imagery. Now we're going to bring in the vegetation analysis that just looks very simple. It's 1 line of code in Earth Engine to compute what you just saw, and now we're running the snow and ice detector. Now, okay, that's interesting. Well, who cares, right? Well, one of our science partners is now using this to look at snowpack over the Sierra, and in fact has determined very efficiently in just a few lines of code you can see the snowpack that was in the Sierra in May of 2010, and then you can see the snowpack as of last month. Where, again, you see pulling down the code window. So that's 2010. And now we'll turn off 2010 and turn on this year. There's the drought. You can see it with your own eyes. Now, so all of those were analyzing one point in time, imagery at one point in time. Where it really gets interesting, since we have years, decades of data, is looking at trends, doing change detection. So this is a fun data set we wanted to show you. We start with, it's called City Lights at Night. There's a particular satellite that is measuring light emission, both visible and a bit of near infrared. And you can see the major cities in Europe, for example. But we have in there, I think, 20 years of data. So we were wondering, well, how are these cities growing or shrinking? So we have an algorithm that lets you do a linear fit, and then you can produce this. Again, in just a few lines of code, and you can see Spain is getting, red means it's growing. The kind of green means it's stable. The blue means it's decreasing. It's interesting, you can see blue in cities like San Francisco and New York, not necessarily because they're shrinking, but because of new policies that are trying to reduce light pollution. And street lights are facing down rather than up. But that big red blotch over North Dakota is the fracking oil fields of North Dakota. I think it's the Bakken oil fields. All right. The European Parliament, member of the Parliament and the Society for Conservation Biology, they came to us because they wanted to map where are the roadless areas of the world, those last remaining places that are untouched by humans, because those are the center of biodiversity, for example. And they had no way to do that. So using Earth Engine, we brought in the Google Maps road data, and we made a measurement of all the areas that were more than a certain distance from the nearest road. This is showing 1,000 meters or 1 kilometer from the nearest road, but the organization wanted to see 10 kilometers. We just changed the code, changed that constant, reran, and you see how quickly it reruns the results. And there it is for the whole world. And they're using that now as an instrument for policy, trying to protect those areas. All right. So you've seen kind of a whirlwind introduction to geoscience, a little bit of what you can do. I just wanted to end with what are some of the amazing things some of our partners are doing beyond forest. Forest was our first use case, but now we're really branching out with these partners. So David Lallemant at Stanford is mapping earthquake hazard using Earth Engine. This one I found somewhat alarming. So here we are, Bay Area. You can bring in vector data, as I mentioned. Here's the San Andreas Fault. He's modeled predicted ground acceleration in the event of a rupture on San Andreas Fault of 7.8 that matches the 1906 earthquake. I asked him, I said, I wonder where I live. So we brought in 2 dots. I don't know if you can see them. One down south is where I live. The other dot is near the Bay Bridge. That's where we are right now. You can see why you might care about having this information. Sea level rise. You may have seen in the news that glaciers are, like the Antarctic is calving these glaciers. Sea levels are already rising in certain places. People need to know what the risk is to their home, to their livelihood, and you can model that now with the digital elevation, modeling sea level rise, where will inundation happen. This is being done with the Australian government and CRCSI. Drought monitoring, very relevant here in California. So this is looking at anomalous heat or wetness or dryness in California for the first 2 weeks of December, last December. And you can see what we all know who live here, that California is showing up bright red because of the tremendous, unprecedented drought that has struck much of the American West. Now, A really important area, it's a little bit more wonky, it's called evapotranspiration, but being able to model how plants are taking up water, how much water they're using. So this is Nebraska over the Ogallala Reservoir, and we're modeling here, this is Rick Allen's team, University of Nebraska and so on. They're modeling where plants are taking up water. Now, this is important for a lot of reasons, like helping farmers and food security, but there's also, we're discovering, a lot of commercial interest now in Earth Engine. We developed Earth Engine as this platform for helping science, helping humanity, protecting the environment, and that remains our huge focus. But we're being approached by, for example, Gallo Winery. They manage 8 million acres of vineyard in California. They try to tell their farmers, their growers, how much irrigation to do. They have 8 people who download Landsat data by hand into a desktop, and they run these algorithms painfully on their desktop that we have fully automated. So they're now trusted testers, Gallo Winery of Earth Engine, and we're really excited to see where that goes. The last one I wanted to show you was emerging infectious disease or global public health. This is one of the more, I think, important ones. We focused a lot on environment. But it turns out that you can predict, by knowing environmental factors like rainfall, temperature, the greening of the landscape that you can see from the satellite data, we've shown you some examples of that, you can predict where mosquitoes are going to hatch, right? Where there's going to be various types of disease vectors 6 or 8 weeks in advance. And with that information, you can mobilize the resources much more effectively. So UC San Francisco is just starting to use Earth Engine to do this kind of analysis. And the common theme that we're hearing from these scientists is they have the science, they know how to do it, but they've been limited to what they can do on their desktop. This is what Gallo Winery told us also. They want to scale, they want to go big, right? They want to go global, and now Earth Engine lets them do that. These are some of our partners. As you can see, they are largely scientific institutions, government institutions, because in fact, as you've probably seen, Earth Engine is a fairly technical platform and API. We're really honored to be working with some of these leading scientists in the world. We do have, again, I said it was an experimental API, and maybe half of you are scared off by what you've seen. This is not a tool that lets you send yo to someone, right? It's kind of the other extreme. So you can cut yourself in this, you know, it's really massively powerful, but you kind of got to know what you're doing, or you could probably get into trouble and make a lot of stuff that doesn't make any sense. That said, we have a sign up. We have our website, there's documentation, there's tutorials, introductory API tutorial, and there's a particular tutorial on the Hansen Global Force data that we think is very useful. So what did I want to say? I think, you know, for a lot of you guys, this technology may be so out there that it's not really relevant, and that's fine. That's great, right? We have really hit a sweet spot with the geoscience community. What I'm excited about is seeing if there is some middle ground. Can we make remote sensing, this type of Earth observation data analysis, transformatively or disruptively easier than it's been before, so you don't have to be a PhD in that field in order to be able to come in with new ideas, contribute something new to this community and to this space, and maybe change the world in a way that no one has ever anticipated before. I know someone in this room is going to do that. I know people watching are going to use Earth Engine, and they're going to change the world. Thank you very much. So we just, I kind of get excited, I kind of go on too long, but we do have a few minutes for questions. So please, come up to there's 2 mics.
Hi, I'm a fellow geodata geek and developer, and I work for a commercial product that allows you to move data around, spatial data around. And so
Okay.
I'm curious about your ability to export those tiles that you've computed with Earth Engine, and I would be very interested to hear more about those capabilities.
That's a great question. A lot of our users have already developed some historic workflow and some other tool chain, but they see the tremendous value of using Earth Engine for the data catalog, for pre-processing, for producing some of the data products they need for their other workflow. So yes, you can produce something and then download it to Google Drive, your own personal Google Drive. You can download it over to Maps Engine, but if you put it in Drive, then you can download it and do whatever you want with it. It's your data. We have data liberation, and this is a good example of that. Yes, a lot of people are doing that. Our goal is to make Earth Engine so rich and so powerful that fewer and fewer people need to take the data away. They can get the job done in Earth Engine, but whatever floats your boat, that's fine. Yes, you're next.
Google has announced their plans to launch large constellations of satellites for communications, but is Google intending to enter the Earth imaging arena also?
So I think you're referring to Skybox acquisition, which we're really excited about, actually, because they are one of those innovative, disruptive new satellite companies. Skybox collects 1 meter imagery. You can task their constellation. They just launched one so far. They have plans to launch more. I think there are a lot of exciting integration points. We can't speculate too much because it actually hasn't closed, this deal, but we can see a lot of really exciting opportunities there. Does that answer your question?
Sure.
Okay. Yes.
I'm involved with a project to categorize road segments by their width, and it seems that this fits with the set of tools you have. Am I correct in thinking that?
If you have access to the high-res data, I think the public data catalog we have, Landsat, for example, even if you pan-sharpen Landsat, it's 15 meters per pixel. And that probably doesn't give you the resolution you want for mapping road width. You're going to need a higher resolution data set. I mean, if we had Skybox data, that's 1 meter per pixel. They're commercial data sets. Now, if you have that data already, right, you could bring that into your Maps Engine account, and you can analyze it in Earth Engine. And yes, you could do that. You could do that. It'd be interesting. We'd love you to try. Yes?
Hi.
Hi.
So 2 questions, actually. The first question is so you did make mention of the fact that you can come up with irrigation strategies as far as agriculture is concerned. I'm just wondering, can Google Earth Engine be used for the purpose of tracking crop yields in rural areas, especially where there are frequent food shortages?
Yeah, no, that's an excellent question. The answer is yes. At least 2 of our science partners that we know of are already doing that, global crop yield estimation. There are tremendous applications of that for food security, as you're suggesting. If you can bring in information about drought, rainfall patterns, understanding something about the nature of the crops, and be able to estimate the yield, it has tremendous positive value, and people are doing that, yes.
Right. So the second question I had was pertinent to how often is the imagery updated as far as Google Earth Engine is concerned? So if you wanted to see what your yield was in the last 2 weeks or 4 weeks, is that level of data available?
Yes. I love to be able to say that. Yes. We have a feed from US Geological Survey. We're getting thousands of images every day from them, from all of their sensors, all the Landsat satellites. We get the data, I think, within less than 24 hours of it being collected. So yes, there is fresh data coming in, available in Earth Engine for exactly that type of purpose.
Wonderful. Thank you.
Yes?
I work a lot. We do a lot of remote sensing at my company.
Yay, there are some remote sensing people here. Yay.
And so I gather that Earth Engine is free to use for nonprofits and for governments, but what about commercial licensing and rights to resell derivative products?
Right. So as I said, our birth was public benefit, advancing science, nonprofit use. We will continue to really push on that. But there are commercial companies that are interested, and we're actually realizing that if you want to change the world, helping the business sector do better management, for example, of their supply chain. So Nestle or Walmart or Unilever or McDonald's can verify that where they're sourcing their palm oil for their Girl Scout cookies is not resulting in illegal deforestation. That's a good thing. So we're just starting this year to work with a handful of commercial companies for free and letting them kick the tires of Earth Engine, but use it commercially. The normal, under a trusted tester agreement, normal license restriction is you use it non-commercially, but if you have a commercial application you want to experiment with, you can contact us.
Okay, thanks.
Yep. But you have to have a good use case, because our team is small, and we want to support the people that we think are going to do really amazing things. Yeah.
Very good.
All right. We have 1 minute left. Who's going to? Okay. Yes.
So two questions. The first one is I'm curious about the plans for improving the support of vector data within Google Earth Engine.
Yes.
And the second is whether support exists for interannual analysis like you would use for computational model building and predictive efforts.
So I misled you. We're actually a minute over. What was the first question?
Plans for improving the vector data support?
Oh, yes. Okay. So today, we integrate with Google Fusion Tables. And so knock yourself out. We have a whole suite of vector operations on Google Fusion Tables. We're also integrating with Maps Engine, Google Maps Engine vector tables. That should be coming out this year. So we should have pretty rich support for different vector backends from Earth Engine. But today you can use Fusion Tables. Interannual analysis, yes, you could do that. But why don't we talk offline so I understand more specifically what you're trying to do. All right, you guys, thank you very much. Go change the world.